So fine guys, let's continue. Okay, so in the last class we have started and we have seen transformations. Okay, and we have seen log transformation. Okay, log transform we have seen, and we also understood uh, we also understood how transformations are helping us to achieve better results. Okay, fine. So now the next concept here is, okay, now it's time to, so that was regarding the functional transforms. Okay, the scalar. So why it's called functional transform? Because we are importing it from the function transformer. Okay, from scalar, scikit-learn. Okay, that is one thing. Second thing comes the power transforms. Okay, so over here you have mainly two types of transforms, guys. One is Box-Cox. Okay, one is Box-Cox, and second thing is Yeo-Jhonson. Okay, so here the fundamental idea over here is, okay, the fundamental idea over here is, see guys, if it is a log, see there are some cases where applying log will give you a normal distribution. Okay, what is our goal here fundamentally? To convert into normal distribution. Everybody agree? To convert our given distribution into normal distribution is our goal. So using log we have seen. Okay, one more method today morning I have also explained you the theoretical part of the reciprocal and also the square root. Agree? Reciprocal is just doing the 1 by x and square root is just doing the square root. Okay, these are fine, but the problem here is which one to go for. Okay, there might be 10 different methods. Okay, but which transformer you should use. Okay, you cannot try all of these transforms all the time. Agree? So that's the reason we have something called as Box-Cox transformer. Okay, these are the two scientist names. One guy is Box and second guy is a Cox. Okay, Box-Cox transformer. Okay, they have come up with a new transformer, Box-Cox, which is a general transformer. Okay, which is a general transformer. Okay, so as you can see here, this is the equation of the Box-Cox transformer. Okay, and from this only, okay, you can derive all these type of functional transformers. Okay, this is a more generalized format. Okay, more generalized format. Okay, just give me a second. Okay, more generalized form of the transformer. Okay, so okay, I'm just getting comments. Hold on, wait. Can you confirm? Okay. Yeah, sorry guys. So now coming to, it's a general transformer. Okay, so the equation is this. Agree? The equation is this. What does this mean? Okay, this means that given any value, okay, the new value will be transformed in this way. Getting? If it is log, what we are doing, guys? If you are giving x, what will happen when you apply log transform? It will become log x. Agree or not agree? When we apply reciprocal x, what will x will become? 1 by x. When you apply square root, what will x will become? Root of x. Agree? Similarly, but the problem here is which one to use this, or there might be so many other. See, when there is possibility of reciprocal and there is possibility of square root, there will also be possibility of cube root. Okay, 1 by x square. Okay, x to the power of 4. Any transformation is possible. Agree? So, but which one to go for? You cannot try 10 types of transformations on, let's say, 10-20 columns all the time. Fine. So obviously there should be some general transformer which will help us, okay, to give the exact type of transformation which we need to perform. Fine. And that general transformer is the Box-Cox transformer. So here, if you see the value, okay, yi will be transformed in this way. Okay, will be transformed in this way using this equation. Okay, where you are using a parameter called as lambda. Okay, if at all this lambda is not equal to 0, if lambda is not equal to 0, it will be using this value. If lambda is equal to 0, it will be using this value. Okay, we'll see what is lambda and how we will to find out the lambda. See, the exponent here is a variable called as lambda that varies. Okay, that varies over the range of -5 to 5. And in the process of searching, we examine all the values of lambda. Okay, finally, we choose optimal value, resulting in the best approximation to a normal distribution for our variable. Okay, simple. So from here, the lambda, see a new value. Let's say you are having a new value of what is the value? Let me take some example. Okay, what is this? That 26. Okay, this 26 needs to be transformed into some other value, new value using Box-Cox. What will happen here? We are going to do 26 to the power of lambda. Okay, -1 by lambda. Okay, but what is this lambda? Box-Cox will itself will try to find out this lambda. Okay, okay. Let's say it has found a particular lambda. Okay, for which the all these values. Okay, similarly, see for okay, now 26 will become what, guys? See, 26 has become what? 26 to the power of lambda -1 by lambda. Agree? And similarly, 54 will become what? 54 to the power of lambda -1 by lambda. Agree? Like that, every value, for example, if I consider age, every value in this age column will be transformed to a corresponding Box-Cox value. Fine. And after that, Box-Cox will try to find out a specific lambda. Okay, same lambda will be same through across the complete column. Okay, for which the new values will follow a normal distribution. Okay, it will find out like in the process of this, what it will do, see, it will range between -5 to 5. Okay, you don't need to manually find it. From -5 to 5, it will experiment. Okay, it will experiment and find out for which particular lambda you are going to get a most nearest possible normal distribution combination. Getting that means what? So if at all, for example, it is taking lambda equal to, for example, 2, for simplicity, lambda equal to 2. Okay, so this 26 will become 26 to the power of 2. Okay, -1 by 2. Okay, similarly, this will become 54 power 2 -1 by 2. Okay, like that, every particular value in this age column will be transformed using this lambda 2. You will have a set of numbers. Okay, I will call that lambda equal to 2. Similarly, it will use, okay, it will try and experiment with different combinations. Okay, different combinations for different types of lambdas. Okay, lambda equal to, let's say, 3.4 or 4.8. Okay, -5 also, it could be some -1.7, some different values from ranging from -5 to +5. It will experiment and it will find out for which particular combination. For each value of lambda, you will have a separate set of column. Okay, because if you replace with 4.8, you will get new value. Similarly, you will get new value. So overall new set of values you will get, which you can call it as lambda equal to 4.8 column. Okay, you will have a new value. Like that, you will have different combinations of new columns. Okay, and it will try to find out its distributions. Okay, among all these different combinations, there will be one lambda. Okay, one lambda for which the distribution will be very closer to a normal distribution when compared to all other lambdas. Okay, I'm not saying it will be the exactly normal distribution, but it will choose the best. For example, it has tried with 10 lambda combinations, and among that, a particular lambda where lambda equal to 3.8. Okay, it is having the most nearest distribution. That means what? Here the skewness will be almost equal to 0, or kurtosis will be almost equal to 0, like that. Okay, it will compare all different type of 10 combinations, and it will give you the lambda according to that particular value, and that will be the lambda chosen for all this column. Is it clear, guys? Are you getting what I'm able to explain, or shall I repeat?
Yeah, repeat. Sorry, Santosh. Understand, but do we need to give lambda value, or by automatically it will
only decide, because you cannot, if you should again give the lambda, then there is no point, because how many lambdas you can try from -5 to 5? You don't need to give any lambda value.
Okay.
It will try. Yeah. It will try and experiment. It will give you the lambda value. Okay. Others, what about you? You understood the theory? Any doubts?
No, sir.
Okay, clear, right? Okay. So if you didn't understand, let me know, guys. I'll repeat, no problem. Okay, but you should understand. Fine. So, but the problem here is, it will work. Okay, it will work only for the positive values and zero. Positive values and zero. The problem with Box-Cox is it will only work for positive values or zero. It will not work for negative values. Okay, it will not work for negative values. Okay, for that reason, you have one more generalized transformation called as Yeo-Jhonson. See, guys, don't worry about these formulas. You don't need to apply. It's just a background scenario what I'm trying to explain. Okay, you already have predefined libraries which you can get it at single step of execution. Okay, all the time. So throughout all the concepts till now I discussed about like 20 to 25 concepts. Everything will have a story behind it, but you just need to understand the story, but you don't need to remember the formulas, or you don't need to derive the derivations, etc. Okay, you already have the Python code available. Okay, so to overcome this problem, okay, what is the problem? Box-Cox works fine, works great. Okay, but the only problem is it doesn't work for negative values, because only lambda equal to not equal to zero, this is if lambda equal to zero, this, but it doesn't work for negative values. Okay, just to make it more generalized, okay, more generalized, you are having one more transformation called as Yeo-Jhonson. Okay, this transformation is somewhat adjustment to the Box-Cox transformation, but only the thing is by which you can apply it to a negative numbers also. Okay, for negative numbers also you can conveniently apply Yeo-Jhonson. Okay, here also the same thing. Okay, here also the same thing, using lambda value. Okay, the lambda will be experimented between a range of values, and it will use the corresponding function. Okay, if lambda equal to not equal to 0, x a given value is greater than, okay, some combinations you have, and the corresponding formula it will use. Okay, it will carry out this execution. It will give you what is a lambda and what type of values it is going to give. It will work for negative values also. Okay, so fundamentally what is Box-Cox doing? Box-Cox is just trying to help you, okay, with a particular parameter called lambda, okay, which itself it will derive. Okay, but ultimately it is telling you what type of transformation, okay, what type of equation you need to use, okay, so that your given values will be transformed to a near normal, or if you are lucky you will get a perfectly normal distribution also. That is a fundamental point. But the problem with Box-Cox is it will not work for negative values. For that you have more generalized transformation called as Yeo-Jhonson, okay, which will have a separate set of equation, but it will also work for the negative numbers. Same scenario, same cinema, nothing changed. Okay, it will also experiment, it will also give lambda values by itself. But the only thing is here, even if your data have negative values also, it work. Okay, for example, here you don't have negative values, age and fair. Age cannot be negative, fair cannot be negative, but there might be some values. Okay, for example, if you take what account balance, okay, if you take account balance could be negative. Okay, if you withdraw more, if you cross your overdraw limit, the account balance will go into negative. Okay, in that scenarios, if that particular column you want to transform into a normal distribution, you need to use Yeo-Jhonson. Anna, నేను చిన్న మీటింగ్లో ఉన్నా అన్న, కొంచెం టైం పడుతుంది. Okay, guys, is the theory part clear so that I can proceed to code? Code will be easy, but just take few seconds and try to understand yourself whether you have understood the theoretical part, whether the concept is clear, the fundamental concept what you are trying to achieve here.
So Santosh, this Box-Cox and Yeo-Jhonson, instead of using those log and reciprocal square root, instead of using, we can directly use this, or
Yes,
this is
yes.
Right?
Yeah, you can directly use this. From this only you can get from this only you can also get like reciprocal or square root. Okay, so using certain value of lambda, you can derive it, but this is a more generalized form, so you can directly use this in place of reciprocal square root.
Okay, fine.
Okay,
so this is one of the transformation method, right? Box-Cox
right,
and
right.
Yeah.
Okay,
Yeah,
but
understood.
most efficient transformation method. Okay, see what is simple transformation, Karthik? It's a very simple meaning of transformation is changing your column into new column. That's it.
Yes,
Simple.
yes.
You have a
Yes.
column, you are changing into new column. By how you are changing? You are doing some, you are applying some transformation. It could be, see, you have this column, right? So if you multiply this column with 2, okay, all this column into 2, if you multiply, you will get 44, some 90, 98, something like that, right? Or that is also a transformation.
Yes.
Agree? You're just
Yes.
transforming the value into new column using certain equation or certain formula. Okay, that is also transformation. You can, there are like 1,000 transformations possible. Fine.
Yes.
Even if you add one value to all of these and you create a new value, that is also a transformation. Obviously, you cannot deny that. Okay. But these are more scientifically proven, statistically evident transformations, which will result you in a normal distribution. Okay. So everything you do, there should be some goal. Fine. If I multiply into 2, you will get a new column. That's fine. It's a transformation. But what is the use of that? What I'm going to achieve? Nothing. But if I do some logarithmic on that, if I do some square root, there is a possibility you can get some normal distribution. Okay. That's the concept. Okay, so shall I proceed for code part, guys? Everyone?
So,
Okay.
yes, sir.
Okay, fine. So now code part is easy. Okay, see, now coming to Box-Cox. See, guys. So I'll give you an overview. Okay, for this, the same thing. The NumPy, Pandas, Seaborn, Matplotlib. I think you are all aware of these libraries by now. Okay, so all this we are going to see. Don't worry. Okay, so you might be aware, but all this we are going to see after one statistics module is completed. Next we will be starting with, say, in this order only: NumPy, next Pandas, Seaborn, Matplotlib. Okay, all these 4 we are going to see. Okay, fine. So model selection, trend test split we have seen. Okay, cross-wall score we have, there is this is just for the accuracy score. Okay, linear regression, R2 score, power transformer. Okay, fine. I will explain you. Now here the data set what I'm using is a concrete data set. Okay, so what is the data set? Let me show you the data set. Okay, where is my math notebooks? Where's concrete? Yeah, so you know the concrete data, I mean the concrete, cement, concrete, construction material, cement. Okay, so all these blast furnace, fly ash. Okay, and what I'm trying to predict, guys, what I'm trying to predict is strength. Okay, the output column is strength. Okay, the output column is strength. Agree? So all these are my input column, and my strength is my output column. Okay, strength is my output column. So that means what, using all these values, I want to predict the strength. Okay, just like how we have predicted using using age and fair, I predicted whether the person is surviving or died. Similarly, here I'm predicting a particular value. Okay, but this is a regression problem, guys. This is a regression problem. Okay, you might be aware or you might not be aware about regression. I am not sure, but let me just tell you. If the output variable, okay, the simple definition is, if the output variable is, okay, if the output variable is numerical, okay, it is regression. Okay, it is regression. But if the output variable is categorical, it is what? Classification. Okay, simple. In the morning, what we have seen survivor example. Here the output is what? 0, 1, either 0 or 1. These are just 2 categories. Okay, don't think that because 0 is a number, 1 is a number, this is numerical. No, because if you remember in our first class, okay, in our first class, when we are speaking about the categorical and numerical concept, so I have told you categorical data are the one which appears in categories, okay, like a group of numbers. But sometimes a numerical values can also be acting as a categorical. So here 0 and 1 are not numerical, they're categories, either 0 or 1. Okay, don't get confused. Fine. So that's why, since there are only 2 categories, either 0 or 1, so it's a classification problem. Okay, it's a classification problem. But now for the power transformer, I'm using this concrete data set where my output is not category, guys. It's not either like yes or no, 0 or 1, pass or fail. It's not like that. See, there are all these are continuous values. Any value is possible. See, all these are different values. Okay, how many unique values are there? So many unique values will be there. But here in the morning exercise, how many unique values are there, guys?
2.
2, right? But here there will be like lots of hundreds, I would say. Okay, that's why this is numerical data, continuous data. Okay, continuous data. Okay, so that's why it is called as regression. Okay, that is a fundamental difference. Okay, before starting to work on any machine learning problem, fundamentally you should know what type of problem you are solving. Okay, if you don't know that, then there is no point. Okay, so because for regression you use a set of machine learning algorithms, and for categorical you use a set of machine learning algorithms. Okay, fine. So now coming back to the main concept. Okay, so now what we are trying to do, I'm just importing this. Fine. And main thing is data is imported, read CSV. I'm seeing the head. Okay, these are the 5 columns. Okay, shape will give you number of rows, number of columns. Okay, fine. Clear. And now df.is.null sum. Okay, so first of all we will see whether the given data is having any null values or not. Okay, why? Because as I told you, machine learning algorithms won't perform in a better way if at all there are any null values in it. Agree? So that's why we will check whether there are any null values or not. Okay, here it's clear that it is not having any null values. Fine, all zeros. Fine. So that's perfect. And if there are any null values, what we are going to do? We will just handle it. How we are going to handle it? We'll do fill NA, and mostly we'll do by mean. If it's a categorical, we go by what? Median, sorry, mode, etc. Okay, that also we are going to see in the module called as feature engineering. Okay, we have a module called as feature engineering and EDA. So there I will be showing you like what all types of handling techniques you can use for missing values, for scaling, everything we are going to see. Don't worry. Okay, so this is, we have seen, okay, no column is having any missing values. Okay, it's perfectly fine. After that, describe is a one function. Okay, so it will just tell you what is the count of each. And so for cement, this is a count, this is a median, this is standard deviation, minimum value, 25th percentile, 50 percentile, 75th percentile, maximum value. Okay, so these are the values. Similarly for every other column. Okay, fine. So this is when you say df.describe, just with small one line code, it will give you the complete picture of the data. Okay, that is how much powerful pandas is. Okay, just by looking, if you spend 5 minutes of time, you will have so much of information about this data. Each and every column, what is the mean? Fine, what is the 50th percentile? Okay, what is the 75th percentile? Okay, like that. Agree. Now, what we are going to do? So same thing today morning. What we have done. First, we need to identify what is input column and output column. Input is X, output is Y. Okay, well, that's why what we are doing. X out of this all columns. See the way how we are taking the input and output. Out of all these columns, what is the output column, guys? Which column we are trying to predict?
Strength.
So only this will be our Y. Agree? Remaining everything will be our X. Agree? So if I just drop strength from the whole data set, I will be left out with only all the other columns, which will be my X. Agree? So that's why, see what I'm doing in this, from this df, I am saying df dot drop. What are the columns I want to drop? Just drop strength. Okay. So when I drop this, the remaining columns from cement to age, okay, this data set, okay, will be called as X. Okay. And after that, how I'm taking strength, guys? I'm taking strength in this way. There's a different ways how you can access, but why what I'm doing? And see, in the morning, we have used this method. Okay, df.ilog. Okay, and I'm selecting all rows, but on which column? -1 column. -1 means what? Last column. Okay, you know, negative indexing. This is -1. This is -2, like that. Okay, so I'm taking only -1 column. Agree? I'm taking only -1 column. Fine. So this is how. So now what has become, from cement to age, all this became my X, and only strength became Y. Is this clear?
Yes, Santosh.
Perfect. And now coming to next thing, what we have done now, we have input. Okay, X and Y is done. After that, once we have input, next thing what you need to do, you need to divide into train data, test data. Using what? We are using train test split. Over here you are giving X and you are giving Y, and my test data set equal to 0.2. That means 20% of test data. What will be my training data set? Training will be 80%. Okay, that's all. Okay, random state is different thing. I'll let you know. Don't worry about this. Okay, so now the whole data X and Y is divided into two parts. One is training data and one is test data. Okay, today morning what I said, I'll explain you. I'll just give a recap. See, you are having a data, train, test. You're dividing. Fine. After that, on this training data, you will do what? Model training you will do. Okay, model training will be done on the training data. After that, using this test data, what we will do? We will test the data and get the predictions. Okay, using test data, we'll test, and it will model will give certain predictions. Okay, from these predictions, you will get the accuracy. Okay, this is the flow. Data separation, train data, test data. Using test, during train data, train the model, get the predictions, get the accuracy. Okay, from where? From the test data. Only train data will be used for train the model. That means model, to generate a model, you will use a train data. Once the model is generated, then you will bring the test data. Okay, you will bring the test data, and then you will test the model on that, which will give certain predictions. Okay, on based of that, you will get the accuracy. Is this clear?
Yeah, Santosh, but I have small doubt in
please,
the ninth line. So X train, X test, Y train, Y test, right? So what are the values will store? I mean, we are giving capital X, I mean, in the split function, we are giving X comma Y comma, right? So here X is completely input
Correct.
and Y is output.
Correct.
So here, how data will be assigning, like X train and X
Okay.
test,
Fine.
Y
Fine.
train and Y
I'll tell you.
test.
I'll tell you. I'll tell you. See. Now, out of this, if you see, from A to H, okay. So let me just zoom this, you'll understand. Okay. From A to H is my X data. Agree?
Yes,
Only Y is my
Y data.
Y data.
Output.
X is input, Y is output.
Yes.
Okay. We did not divide the data into train data, test data. We just said for any machine learning model, there should be input, there should be output. X is
Yes.
input. Okay. Oh, that means input is having so this cement will become X1.
Yes.
Blast furnace will become X2. Okay. Inside X there might be anything. Okay. But Y will
Yes.
always be only 1 because
Y.
output value will always be only Y. You cannot predict two things at a time.
Yes.
Okay. Clear. Everybody clear? This point we'll go step by step. Okay. I will again explain this train test split when we are studying machine learning in very much detail. But now since Karthik has raised this question, we will have a basic understanding. Okay. Are we good, everybody? X and Y.
Yes, sir.
Okay. Now see. Now what will happen? X and Y is there. Now you are passing this X and Y. Okay. You are passing this X and Y. Just a second. Okay. You are passing this X and Y to train test split. Okay. To train test split you are passing, and it is dividing you 4 things it is giving you. How it will divide means, see, it is very interesting. This is X. Okay. Overall, let's say this data frame is having only 30 rows, for example. Okay. It is having so many rows, but for example, let's say it is having only 30 rows till 30 only, from 1 to 30. Now, what will happen? What will happen means it will divide in this way. Okay. When you, how much percentage you are dividing is? How much percentage? 20%. Okay. That means what? Test size is 20. 0.2 means, that means training size is 80. Okay. So roughly out of 30 rows, test size is 20%, means, for example, let's consider 10 rows will become test data. Okay. 20 rows will become train data. Okay. Are we good?
Yes, Santosh.
Okay. Or are you getting confused? Fine. If you're getting confused, let me say 20% is how much? 30 rows, 20% is how much? In 30 rows, 20% is 6 rows. Okay. So 1, 2, 3, 4, 5, 6. Okay. From 25 to 30, these 6 rows will be test data.
Test.
Okay. And from these rows will be train data.
Train.
Yeah. Okay. Okay. So let me write it here. Okay. So this is X and only X is Y. Okay. So from here, this is train. From here, this is test. The division will always happen between the rows, guys. Okay. Between the rows. It will not divide with respect to columns. Okay. Because in even the fundamental point you should always remember here is whether it is training data or whether it is test data, both of them will have all the columns.
Yes, including
Okay?
Y also.
Including Y also, because see, whether it is X or Y, okay, when I'm saying training data from 1 to 24 is training data, that means what? All the columns from cement to strength, okay, cement to strength, all of these columns should be present in training data and also test data. That means what? Division will be happening based upon only rows. Some rows will go into training data, some rows will go into test data, but all the columns, including input columns and output column, should and must be present in both test data and training data. Clear?
Yes, Santosh.
Everybody clear? Any confusion here?
Clear, sir.
Okay. So now after that, what that's it. Simple. So now this has become training data. This has become test data. Next what? Very simple. Now, yeah. So now what will happen? From A to H, this will become, okay, this part from A to H And from 1 to 24, this is what? This is X data and also training data. Agree?
Yes. Train X.
Right. And from 1 to 24, only I row, only strength row, this will become Y
Train.
train.
Y train.
Agree?
Yes.
Because this is Y, but it is train Y.
Yes.
Similarly, this is X, but that is train X. Agree? Cool. Similarly, now from 25 to 30, okay, from again all columns A to H, okay, A to H, okay, this will become X. These are X only, input only, okay, input. But which input? Test input.
Test input.
Okay, and
X
just
test,
this
Y,
one will
Y
be
test.
Y. That means
Test.
output, but test Y. Okay, this is how the division will happen, guys. So we got X train, Y train, X test, Y test. If you see, even in training data also, you will have both X and Y. Test data will also have X and Y. Okay, but in training data, you will have again input train data, output training data. In test data also, input test data, output test data. Is that clear in everybody?
Yes.
Okay, fine. Sirisha, doubts? Okay, fine. Okay, this is how the data will be divided. Okay, the same thing is happening over here. For example, if you see X and Y, you are giving X train, X test, Y train, Y test. Okay, so first it will give X value. Okay, don't get confused. Okay, it will give first both X values and then it will give you both Y values. Okay, but actually among this X train and Y train are input data. Sorry, the training data, and X test and Y test are test data. Okay.
Okay, but my doubt is,
Yeah.
in function we have given capital X comma Y both, right? So
Yeah, you are giving X and Y input data and output data.
oh,
You are giving. You are just giving what? You are just giving. Okay, so you are just giving all data. So you are saying from A to H is my input and only I is my output. That's what you are saying to the function.
okay, 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 okay,
Okay.
okay, got it.
If you see here, because first of all, it should understand which one is output, which one is input, right?
Got it. Yeah.
Right. Okay. So that's what we are saying. Okay. Just consider this as input. This is only Y. That's what we are saying and we are telling. How
Yeah, I
it is
got
going to
confused,
divide?
like, yeah.
Right. So how it is going to divide? It will envish. Okay. This is how it will divide. Okay. Always try to remember this picture. X train will also have X train, Y train. Test will also have X test, Y test. Okay.
Sure.
Fine. And now coming to next point. Okay. So you got X train, Y train, X test, Y test. Okay. As I said, this two will be training data, guys. X means input train data, output train data. Input test data, output test data. Clear? Cool. That's fine. So now what we have done, we have just imported the data, saw some null values, and then we have divided the data, created the input and output, and then created the train data, test data. Cool. Now, without applying any transformation, let's apply some model. Okay. Now, since the output is continuous data, we need to apply regression problem. Okay, regression model. And one of the famous regression is linear regression. Okay, we will see it later, but just assume this is a one regression model. Okay, for continuous variable. And we have loaded this model and we are just doing fit. Okay, passing what data? So this is important. Okay. Now, since you understood these concepts. Okay, let me just revise. Okay, here. So now, as I said, for the model will be trained on what? Training data. That means what? X train, Y train. Okay, you will give X train, TR train, and also Y train. Okay, because model training data, the name itself is saying training data means this data will be used for training. Fine. So you will pass X train and Y train, means X input, Y input you will pass. Model will do what? Will do fit. Fit means train. Okay, we'll see, but I'm just giving an idea. Once model is trained on the training data, after that, you will use what? You will use a test data. You will use a test data for predictions and accuracy. Okay. This test data, X test and Y test will never be used for the training. Test data is only for testing. Train data is only for training. Clear?
Yes.
Okay, fine. Now going back here. So same thing. See, X train, Y train. This is your training data. This is your training data. Both you are using for the model. Okay, X train, Y train. Came here. Model LR is my model. Linear regression dot fit means it will fit the model. Perfect. With the single line, model fitting is done. That's how simple machine learning is. Code part is extremely simple, guys. I'm telling you, you'll also realize when we are discussing machine learning. Code part, the initial basic models code part is extremely simple. 10 lines of code. Literally, I will show you just from 1, 2, 3, not more than 10 lines of code. The whole model will be generated along with the predictions and accuracy. Right from data importing to model pre-processing and data pre-processing and model importing, model building, fitting, okay, and predictions, okay, and accuracy score. All this will be done in just 10 lines of code. Any model you give me, linear regression, logistic regression, decision trees, random for anything. Code is very, very simple. Okay. So don't worry about the code. You can train very easily. You can train any model. Okay. But how the model is working, why you are choosing that model, okay, those will be the important concepts. Okay, fine. See here, how easy it is to train. Model import, fit, okay, training, that's it. After that, once the training data is used, okay, now X train came here, Y train came here, so these are used. Okay, training is done. Remaining left is what? Test data. So here for testing data, you are using what? You are using test data. Okay, X test you have given. Okay, so now you got predictions. Okay, these are the model predictions. These are okay, and then this model predictions. Okay, you will compare with the actual Y values of the test data. So this Y test will come over here, and this Y pred will come over here. Okay, so using these two, you will get some predictions. Fine. So you will give X test, model will give Y pred. Using that Y pred and this Y test, you will find out the R2 score. That means it's an accuracy score. Okay. So what is accuracy score? 62%. Without applying any transformation, simply you're passing the whole data set and training. Okay. That means what? So you are training, you are predicting the strength value by using all these columns. Okay. So you are getting accuracy of 62% is accuracy. Is this clear, guys? Let me know till this point.
Yes, sir.
Okay, perfect. So now we will apply some transformation. Okay, but before that, plotting the dist plots without any transformation. Okay, by default, without any application of transformations, how does my transformation, so how does my data set look like? Okay, so we are using what? Dist plot we are using, and also we are plotting probability plot. Okay, that means what you will get the QQ plot also for each and every column. Okay, see guys, now see cement. Okay, now I want you guys to tell me whether this is near to normal or not. Okay, what do you think, guys? Cement, is it okay? Is it near normal or is it very far from normal?
Yeah, Santosh, it seems like normal. Okay.
Okay.
Yeah.
Fine. And what about blast furnace?
No, this is not far normal.
Okay, this is bad from the far away from the normal. Okay, what do you think by fly ash?
No.
Right, because you can see the distributions also. It is completely left skewed.
Yes.
Correct.
Right skewed or right skewed.
Right skewed. Correct. Okay, and also here this is also bimodal right skewed.
Yes.
Okay, what do you think about the water?
This is okay.
Fine, this
normal.
is almost very good, very good, like it's toward the normal. Okay, what do you think by super plasticizer?
No.
Fine, coarse aggregate.
Yes.
Right, almost fine aggregate.
Yes.
Right, and age.
No.
Right, the worst thing is age. Agree, it is very much disturbing when compared to normal. Fine, but all other, so this is fine aggregate is actually very much near to the normal. This is also actually very good with respect to normal. This is bad. Okay, this is okay, this is not okay, this is not okay, this is okay. Okay, fine. This is without any transformation, guys. We did not come to transformations yet. Okay, fine. Now the main sigma starts here. We are applying the Box-Cox transformation. Okay, so now the power transformation, from where we are getting this power transformation? Can you remember? From here, sklearn dot pre-processing import power transform. Okay, so always try to go through the official documentation. As I said, now if I show you the official sklearn pre-processing power transform, so here it is saying apply a power transform feature wise to the data to make data more Gaussian like. What is Gaussian? Gaussian is nothing but
Normal distribution.
Normal, perfect. Okay, Gaussian distribution is just normal distribution. Okay, so you're applying a power transformation feature wise for every feature. Okay, feature is nothing but input, guys. Okay, for each and every input to make the data look more Gaussian. Okay, so now as I said, every parameter will have a default parameter. Okay, for what does this take? This takes only two things. So one is method, standardize, etc. What is method, guys? Method it could be what all values it can take, Yeo-Jhonson or Box-Cox. Okay, Box-Cox, fine. So now but default value is Yeo-Jhonson. That means you don't give any value, it will take Yeo-Jhonson. Okay, similar like to the what is it, the QQ plot over there. If you don't give any value to the dist parameter, it will take normal distribution. But if you want to give specifically uniform, you need to give uniform. Agree? You remember? Forgot. Here, dist parameter. Here, if you don't want to give anything, it will directly check with the. Here, I'm not giving any parameter. It will check with the
Normal.
uniform. But if you want to
Yes.
give uniform, you need to specifically mention as uniform. Okay. Similarly,
Yes.
here also, if every parameter will have default parameter. Okay. So here method, if you don't want to give anything, just leave it. It will consider Yeo-Jhonson. But specifically, if you want to use Box-Cox, you should give Box-Cox. Okay. Now, what is the main difference, guys? Yeo-Jhonson works with positive and negative values as well. Okay. Box-Cox strictly works with positive values. Okay. Fine. Now, coming to my concept. Okay, so where are we? Yeah, so applying now, I want to first show you the Box-Cox. So that's why specifically I'm mentioning Box-Cox. If you don't use Box-Cox, it will take what? It will take Yeo-Jhonson. Okay, fine. So I'm giving Box-Cox. So over here, okay, what I'm doing X transform. Okay, I'm doing X transform. Okay, PT dot fit transform. Okay, PT dot fit transform. X train, fine. X train is, I'm just doing what? X train is for every value of X, I'm just adding, okay, I'm just adding a small value so that it will not work for
Zero. If you have zero, it will work.
correct. So because Box-Cox strictly works with only positive values. Okay, Box-Cox strictly works with positive values. Fine. So that's why if at all we have, just in case if at all you have any zeros, okay, any zero values, okay, it will have a problem, right? So that's why you are adding very small minute value. This will not change anything, but this will make sure that the value is not equal to zero. Okay, so this will, even if it is zero, now this will be treated as 0.00001, okay, which is negligible, but our issue is solved. We can still make Box-Cox working for this. Okay, so you said it will work for zero also. Okay, oh, did I say that? Then let me go back. Okay, let me go back. Okay, no guys. Okay, if I said that's my mistake, okay, sorry, but strictly it will work for only formula second one. Okay, this one, this is Yeo-Jhonson, Sirisha, this is Yeo-Jhonson formula second one. Okay, this one, okay, yeah, this is lambda. Oh, see, lambda is different. Lambda is not, lambda is the parameter. Okay, see, okay, I think if you're getting confused, let me repeat. The value is yi. Okay, the input value, whatever you are using, what each value is yi. Okay, it is yi. Fine. That should be, the input value should be positive. That should be positive. Okay, but okay, but the lambda parameter, okay, to which power you should raise, what type of transformation you should do, we are having a parameter called lambda. Fine, that could be zero or that could not be zero. Okay, so if that was a confusion, let's try to clear that. Okay, there are two things. One is the input value, whatever you're trying to give. Second thing is a parameter. The input value should be strictly positive. That should be strictly positive. Okay, it cannot be negative or zero. Fine. So, but the parameter lambda, what you are using, right? So if it is zero, you will use this function. If it is not equal to zero, it will use this function. Okay, that is difference. But fundamentally, the point whatever the input we are passing to Box-Cox, that should be strictly positive. I hope that's clear. Okay, now coming back. So yeah, fine, Sirisha, you understood, right? Okay, so now since it works strictly for positive, if at all there are any zero values, okay, if at all there are any zero values, it will again become more than zero. Fine. Same thing for X train also, for X test also, we have applied these transformations. Okay, and we got new transformations. Okay, we got new transformations. Okay, this is transform data. Fine. So see, PT is a power transformer. In that we are using Box-Cox, and to this Box-Cox. And when I say Box-Cox, what will happen, guys? Okay, just visualize Box-Cox. When a moment I say Box-Cox, it will use this complete formula and it will start experimenting with different values of -5 to 5. Okay, if it is equal to 0, if it is thinking that the value is coming to 0, it will use this function. If it is not equal to, okay, if the value is not equal to 0, okay, then it will use this function. Okay, it will come up with some lambda values. But finally, it is working on strictly positive values. Okay, and finally, it is going to tell you the lambda values also. Okay, see, when I'm saying for extend columns, okay, for extend columns, okay, if I'm printing the lambda values, see, these are the lambda values. So it is saying for cement, I should use this lambda. That means what guys? We're getting y lambda minus 1 by lambda. Okay, what is the formula? Y to the power of lambda minus 1 by lambda. Okay, so for cement, it becomes y to the power of 0.177 minus 1 by 0.177. Every value in this cement will be converted to a corresponding value such that you will replace each and every value. Let me just close this, guys. Okay, yeah. So, okay, you will replace each and every value. Every value will become y, and you will replace y over here. Solve this equation, you will get a new value. Like that, once you do for all the values of cement, the new set of values, whichever you are going to get, let me call it a cement lambda, these new values will be near normal. And for that, you need to use lambda 0.17. Okay, it is experimented and it is given you use lambda 0.17 to get a new set of values for cement, which will follow a normal distribution. Similarly, use use what? 0.025 for blast furnace. You'll get another equation and do it for all the columns for blast furnace. All the values in the blast furnace, use lambda equal to 0.025. Similarly, fly ash minus 0.03. Like that, these are the different column values, which will create all new set of cement lambda, blast lambda, fly ash lambda till age lambda. Okay, such that new columns will be almost near lambda, near normal distribution. Is this clear, guys? Let me know if there is any sort of confusion.
Yes, Santosh. So it will give from the transformation, it will give lambda value.
Correct.
Which lambda value we need to use for that column?
Correct.
Okay.
No. It will transform the values. It will see when you just say fit transform and pass the X train. Okay. So here you are adding plus 0.01. Okay. If you are very sure that there are no zero values, Karthik, you don't need to do this one. Agree?
Yes, correct.
Okay. So just assuming that there are no zero values, you are not doing this. You don't need to say anything. Just for this PT, that means power transform, say fit transform and give your X train. It will calculate internally for each and every column what is the corresponding lambda value, and it will transform the each and every value, and it will create the new set of transformed values, and everything is present in this X train transform. Don't think it will only give you lambda values. Again, we should take that lambda values and do individual transformation.
Okay, got it. For just our reference purpose, we have
for
displayed.
your understanding, I have just wrote this so that you will know what type of lambda it is using internally. But no need to use this. Okay, so it will only take the formula, apply experiment with lambdas for each and every column, find out the best optimal lambda, and transform the column and put it in this column. Like that for every other column. The whole new data set will have X transform. Okay. Similarly for X test also, because both X train and X test both are inputs. This is test train input. This is test input. Okay. So for this also you need to do transform. For this also you need to transform. Okay. Is this clear, guys?
Yes, sir.
Okay. Box-Cox is an inbuilt method, sir. Sirisha is asking. Yes, Sirisha, it is inbuilt. From where we are getting power transformer, we were getting, right? Power transformer is inbuilt in the sklearn. Power transformer, you have a sklearn library. In that pre-processing, you have power transformer. Inside that power transformer, if you give method as Box-Cox, it will use this particular transformer. It will use this formula, everything. Is that your question? Okay, fine. So now if you're able to understand the importance of this, see, if at all there is no Box-Cox, how you will find out this? Because for every column, only the simple log transform, reciprocal, square root will not work, obviously. Okay, so you cannot try with different combinations of I would say square root, cube root, or different type of transformations. You cannot do. Obviously, you cannot find out, okay, every time. That's why Box-Cox will take that effort and it will give you every lambda value. You don't need to do anything. Okay, corresponding values it is given. And okay, and you can just experiment. Okay, so I'll show you. Okay, so up now after this this is done. Our new data set is what? Our new data set is extend transform. Okay, so now we are going to train with what? Extend transform. Okay, earlier if you see, we have trained with what? We have trained with only extend, and the output column is same. As I said, we will not touch the output column. Output column will always be same. So earlier, without any transformation, we have just used X-train and Y-train. Okay, we got 62%. Now we have used the transformation, Box-Cox transformation, and we got X-train transformed column, and we are using that X-train transform column, and the output column is the same. Okay, but while predicting, you are using the Y-test transform. Sirisha is saying, in which scenario we know that which transform is going to be used. That's what Sirisha, because we don't know which transformation we need to use. That's why if you use Box-Cox, it will only tell you which lambda you need to use so that the given column will be converted into normal distribution. Okay, Box-Cox is not one single transformation. It is a general transformation. Every new value, as per the lambda value, every new value of lambda will create a new set of transformation. If lambda equal to 1, it will become y minus 1 by 1. If lambda equal to 2, it will become y square minus 1 by 2, like that. So this is a different transformation. This is a different transformation. For each value of lambda, it will create a new transformation. Okay, so you don't know which number for lambda value will suit best for that particular column. Box-Cox. That's why when you use Box-Cox, it will experiment and it will find out and it will tell you what type of transformation using this formula. That means what lambda value you should use so that you will get a perfect transformation, so that the output will be normal distribution. Okay, it's not a fixed transformation, Sirisha. See, if it is reciprocal, it is just you should do 1 by x, nothing else. If it is square root, always do x to the power of 1 by 2 or square root of x. If it is log, always just do log of x. Okay, but in Box-Cox, it's not like that. It's a general. That means y to the power of lambda. What is this lambda? I don't know. If you use lambda 0.5, it will become new equation. If you use lambda 5, it will become another equation. So lambda changes. Okay, so it is a general transformation which you should experiment and find out what value you should use so that you will get the normal distribution. Is that clear? Sir, I'm asking silly questions. Sorry, sir. No, Sirisha, that's fine. Those are not silly questions. Okay, they are actually very good questions. Okay, if you don't ask questions, then that's the problem. Okay, so that's nothing like silly question or stupid question. Okay, fine. So if you're able to understand the concept, that's fine. Okay, so only when you're interested, right, then only you'll ask silly questions. Okay, that's fine. Don't think anytime, and not only Sirisha, anybody. Okay, so I ask more than silly questions than this. Okay, so anybody, if you whatever doubt you're having, right, whether it is silly, small, okay, that's not the point. Okay, clarifying is the point. If you neglect silly, that will only become serious. That's the point. Okay, fine. So is this clear, guys? Everybody, how Box-Cox is helping us? How to find out the lambda values?
Yes, Santosh, understand.
Okay, fine. So now after using once we have the transform data, you're using extend transform. Okay, then you got this, and for return also you are using x-test transform. Fine, you are using y-pred. Now R2 square. So you got 80% is your score. So very good score. When compared to without any transformations, okay, without any transformation, you are getting 62. But once you have applied transformation, okay, you are getting what? 80%. Straight 20%. That's a very good improvement. Fine. But also let's see, okay, without applying transformation, this is our QQ plots, etc. Okay, without any transformation. But after applying transformations, okay, let's see how does our data set look like. Okay, see, for example, here if you see cement, okay, it's okay. Okay, and blast furnace, okay, it is somewhat better. See, fly ash, it has become bimodal, or it became a bit better normal. Okay, for water, more or less same. Okay, but for super plasticizer, it became more normal. Okay, see, this is right skewed. Okay, this became more normal. Okay, so in diabetes project, if I use this transformation, can I change accuracy? Yeah, you can try. It should be okay, but it depends. It depends, as I said. Okay, for every model need not expect this type of transformations. Okay, for example, because linear regression, logistic regression. Okay, these type of models will expect the data should be normal, etc. But if you go for, I think we have used decision tree in your diabetes prediction. So this type of models or random forest or boosting, bagging, some advanced models, it doesn't okay affect whether the data is a normal distribution or not. But still, if we have used logistic regression in your diabetes prediction, you can just give it a try and see. Okay, if you are getting better results. Okay, fine. So super clusters is working great. Course, it is more or less same. Okay, and fine aggregate, okay, it's more or less same. Okay, and age, okay, age, I think it's a better improvement. Okay, because it's very disturbed. Okay, here at least we are having some sort of normality. Okay, fine. So this is, but here I have shown you just the distributions. Okay, but you can just find out the QQ plots also. Okay, use this code. Okay, use this code and just try to see before and after QQ plots. Okay, in the morning exercise I have shown you, right? So yeah, before and after QQ plot, right? Before and after QQ plot. So you can use the same code and you can try to observe before and after QQ plots. Okay, fine. I'll share these notebooks. Okay, don't worry. I remember I need to share all the notebooks. Okay, fine. So that is how your data is got transformed, and the transformed data gave you better results. Fine. Using Box-Cox. Is the example clear, guys? Any doubts, questions? Anybody? Let me know.
Fine.
Okay. Great. So now the other thing is, as I said, Yeo-Jhonson. Okay. So in the scale power transformer, you are having one in this method parameter. You can give by default. It will take Yeo-Jhonson. Okay. That means what? See, if you don't give anything, it will take Yeo-Jhonson by default. Okay. But if you want to give specifically, you should use method equal to Box-Cox. Otherwise, you can just remove this, just open and close parenthesis. It will default take Yeo-Jhonson. Okay. And same thing. Concept is same. So now PT1 is power transformer. That means Yeo-Jhonson transformer. And on this, we are using fit transform, giving X train, fit transform, X test, new transform data, transform 2, transform 2. Okay, train transform 2, test transform 2. You are getting two values. Fine. And on top of that, okay, linear regression. Okay, on top of linear regression, you're using linear regression for this. Okay, LR fit train, X train, Y train. Okay, and simple model loading, fitting. In the case of fitting, you're fitting on the transform data. Okay, and LR dot predict, you are doing predictions and you are doing the accuracy score. Fine, accuracy score. And next, what? You're using the data frame. And now if you see, same thing. So just how the Box-Cox has given you the lambda values, Yeo-Jhonson will also give you the lambda values. Okay, it is saying use this lambda values. Okay, use this lambda values to get the corresponding distributions. Okay, and for this the equations will be over here. Okay, if lambda is not equal to 0, you will use this formula. If lambda is equal to 0, if x is greater than 0, you will use this formula, because here your x can be positive, negative, 0. Agree, guys? In Box-Cox, your value should be strictly positive. That means only positive. Okay, that's why you are not specifying any x value, because by default it should be positive. But in Yeo-Jhonson, it could be negative, it could be 0, or it could be positive. Okay, so that's why if it is greater than or equal to 0, this one, greater than or equal to 0 and lambda equal to 0, this one, less than 0, this one, less than 0 and lambda not equal to 2. Okay, different types of functions it will use internally. Okay, it will try to check what values are getting passed. X is input over here and y is a lambda value. Okay, so it will try to see what are the values cement is having, and finally it will come up with some specific value of lambda. Okay, so these are individual lambdas, and using this you will get some new transformations. Okay, and you can also spend some time and see the new transformation. So I'm saying new transform, right? So you can just try to print this X-train transform and have a look at the new transform values. Okay, in this you will have each and every new transformed value of cement, blast furnace, fly ash. Okay, and just look at them, how the actual cement value. Okay, these are the actual cement value, and how does Box-Cox transformed value of cement is looking like, cement Box-Cox, and how does cement Yeo-Jhonson is looking like. Okay, and try to plot this, try to plot this, try to plot QQ plot, try to plot QQ plot. Okay, so using this makes your hands dirty so that you will have better practice. Okay, and so these are the values. That's it. Now what we're doing, okay, and when you train the model, okay, on this you are getting 81% of accuracy. Okay, so yeah, so it's a linear regression with the Box-Cox transformation. You got how much? 80. Okay, by default without any transformation you got 62. With Box-Cox you got 80, and with Yeo-Jhonson you got 81. These are its corresponding values. Okay, and if I just show you same thing here, what the before and after Box-Cox. Okay, this is the actual raw data, and what is this? This is a corresponding transformations. Okay, so cement looking okay, fine. Blast furnace, okay, looking better. Okay, this got rectified. This okay became little normal. This is more or less same. Yeah, this became almost normal. This not much change. This okay, but age again better improvement. Okay, this is almost skewed. Okay, this is almost like a normal. Okay, fine. So this is a Yeo-Jhonson transformations. Fine. So now okay, you can just have a look at one view. These are the actual columns. Okay, and Box-Cox lambda values, Yeo-Jhonson lambda values. Fine. And for this you will have set of cement Box-Cox values and cement Yeo-Jhonson. Similarly, each and every column Box-Cox value, Yeo-Jhonson value. Its distributions, QQ plots. Okay, so that's how you can, given a data, okay, you can transform, see the values, Box-Cox, Yeo-Jhonson. Okay, is it clear, guys?
Yes, Santosh.
Everyone? Okay, fine, guys. Oh, fine. So that's about the transformation, guys. Okay, so I hope it's clear. Fine. Just go through the code once, go to the class and try to understand the code. I'll share the notebook also. And main thing is, yeah, so as I said, try to okay revise or at least make some notes till the concept which we have discussed till now. Transformation, normal, etc. Fine. So with this I'm going to conclude the transformations. Okay, we have seen major transformations are these guys. Okay, so if you know Box-Cox and Yeo-Jhonson, so everything will fall inside this only, either Box-Cox or Yeo-Jhonson. Okay, you don't need to go for any other transformation. Okay, so you can try to apply it for any data set. Okay, fine. So now once this is transformation is done, right? Fine. So next thing I think we will be starting with something called as central limit theorem. Okay, and but before that there is one two small famous distributions called as Bernoulli distribution and binomial distribution are there. Okay, two type of distributions. Okay, and these are important distributions, and I will give you an example of this. Okay, very simple interesting distributions, and post that we are going to conclude second level of statistics. Okay, so till here it was first level, like till quantiles. Okay, from distribution it is second level, and once this is done, right, Bernoulli binomial, so we will conclude the second level of second level of stats. Okay, then we will go to the third level, so where we will start understanding more about the advanced concepts like central limit theorem. Okay, which is, as I said, like magical theorem which will help you in many ways. We'll see, and from there central limit theorem, then from here we will understand something called as again we will see the concepts like what point estimate, okay, and population sample we'll see. And then the main concept we are going to study from here is called confidence levels, confidence intervals, and finally you will see hypothesis testing. Okay, so there are like more two, 3 levels are pending in statistics. Fine. So, but we'll go step by step. Okay, but the next classes will be little bit advanced, and it will require a bit of more attention, I would say, because that will be a bit advanced statistics. Okay, but no problem. We'll try to make it as easy as possible. Fine. So yeah, guys, but that's all regarding the transformations. Okay, so I hope you are following. Okay, try to have a picture in your mind. From where did we start? We start from normal distribution, detecting normal distribution, and transforming normal distributions. Okay, all these things try to revise. That's all I would say. Okay, so fine, guys. Are we good? Everyone, any doubts, concerns?
No, sir. No doubts.
Okay, great. So thanks guys, thanks everyone for joining. Okay, have a nice Sunday. Let's meet on Monday, same time, and carry on with next concepts. Okay, cool. Thank you guys. Bye.
Bye, sir.